So last two lectures, excuse me, last two lectures we discussed mass conservation and then momentum conservation, and we derived the form of the conservation law for mass and momentum in both material and spatial coordinates. This today's lecture we are going to look at the third piece in this puzzle, energy conservation, because whenever you are doing analysis, you are looking at mass, momentum and energy primarily, and then there could be other quantities which you care about, like angular momentum, or it could be entropy, or quantities that come later. But at a basic level, learning about energy conservation is important, and that's what we are going to do today. And effectively, today's lecture will be the last time we discuss a topic. The next lecture, I just want to do examples. So I'm trying to have a discussion about thermodynamics today. And as usually these discussions go, we go back to the basic of this whole continuum mechanics topic, which is, can you tell me what is the core idea we saw from the very first lecture about continuum mechanics, that we live in a universe which is made up of individual units called atoms. Atoms are discrete entities, but what is a continuous medium? How did we define it? Our continuous medium is a fictional or a imagination of ours, which is an idealization of ours, in which the material is infinitely divisible. That is, you can take a piece, keep dividing it in half. In reality, you know, at some point you will encounter intermolecular or interatomic distances, and the material will stop being a smooth material. It will start having holes. But in our idealization, the continuous medium is something which is infinitely divisible, so that at every point a quantity called the field variable is defined, continuous, differentiable and analytic. So that is the core idea. So when we talk about thermodynamics, we still have to address this disconnect, which is, what are materials made of? Atoms. When you stick a thermocouple in a gas or touch it on a solid surface, you are measuring a temperature, right? We first need to discuss, or this maybe has not been addressed before, unless you took some kind of a statistical mechanics class. What is temperature?
The vibration of the molecules, it's like how fast they're moving, but staying localized. I call it vibration.
Okay, so you are saying temperature is a measure of how much are the molecules vibrating. Okay, any other thoughts?
It's kinetic energy, average kinetic.
Average kinetic energy. Okay. Okay. Any other thoughts? Anybody wants to add something to that? So let me pose. Both of you are correct in a way, but we want to qualify that answer. What are basic quantities? Things that you can observe. You can observe motion. It's easy to think of displacement. It's easy to think of velocity. Those are directly observable or conceivable quantities. But what is temperature? Can you observe temperature? You talked about energy, you talked about motion. How do you go from there to a temperature? How did you come to that scaling that the degree of vibration or the amount of kinetic energy is temperature?
The speed of atoms colliding each other.
Okay, this is our pretty much like nearly last lecture. You should tell me more than few phrases.
Speed of the atoms or molecules colliding each other at a rapid speed.
Okay.
So when there are number of atoms in the particle, so at what speed or what force the molecules collide with each other gives us a certain amount of.
So are you saying energy is like a measure of speed or force now? You're saying that. Okay. Okay, so we have some conflicting views about what is energy, because you can't tell what is temperature without talking about what is energy. So, is it vibration? Is it, when you say kinetic energy, I assume you meant translational motion, like how fast the molecules are zipping around.
Moving, but it will have a different velocity. So that's why we are taking an average. Yeah.
Okay, and you talked about speed or force. Let me just say it's not about force, it's somewhat related to speed, which is how we define kinetic energy. So you two are kind of similar. And when you say that, since you talked about the molecules zipping around, you are thinking of a liquid or a gas, and you talked about the molecules vibrating in place. So in your imagination, it's like a solid you are thinking about. And which is what my question was about: what happens if you stick a thermocouple in a fluid or touch it on a solid? Your thermocouple reads some temperature, 450 Kelvin. What exactly is it reading? That is what we want to answer. What does that 450 Kelvin mean at all?
Average kinetic energy. The average kinetic energy.
The average kinetic energy of the atoms or molecules. Okay, then your atoms are numerous. They are like 10 power 23 in number, roughly, and they are all zipping around. You touch your thermocouple, it reads out a single value. Whose energy or whose temperature is that value? Is it of any one particular atom, or is it like an average over time? What is it?
Average over time.
It's an average over time, right? So in continuum mechanics, or at least in the distinction between what we call continuum mechanics and what we call statistical mechanics. That is, statistical mechanics is sort of like the cousin of continuum mechanics, where you talk about the motion or statistics of individual motion. Here in continuum mechanics, we lump everything and talk about field variables which are continuous. There we talk about averages of quantities which are discrete, like position or velocity and so on. So the basic term, first of all, is there are quantities which are microscopic observables, and then there are quantities which are macroscopic observables. That's the first term that we are going to learn today. We are going to write microscopic quantities versus macroscopic observables. I started with one example, like temperature, which makes sense only if you have certain enough number of atoms or molecules. Like, think about it. You have a beaker of water. You stick a thermocouple probe in. You are going to read a temperature, like let's say 25 degrees Celsius, and it represents the average energy of all those molecules, because they are all kind of jiggling around. At some point, they will all come in contact with that probe, and you are reading out their average energy. Now, imagine you have a water vapor, you have a water molecule which has evaporated and it's moving around in the gas phase. A single molecule. Does it make sense to define a temperature for a single molecule? When you think of an individual atom or an individual, let's say, water molecule, you can think of a velocity for that water molecule. That would be a microscopic quantity. You have velocity, you have position. Macroscopically, you are talking about an average. So these macroscopic observables are averages over a large number, where n is practically infinity, of atoms. Another example would be pressure. When you take a tank of fluid and you say static pressure at a point, what exactly is static pressure? How do you think about it? What is static pressure? You have heard of it in your fluid mechanics classes. If you take fluids classes, this is what they'll teach you. If you put an imaginary surface, the molecules will be, so then the molecules are all randomly moving around. We know that. If they hit a surface, they are going to bounce off this surface. So if you put an imaginary surface, it is the force experienced by that surface divided by the area of the surface. And when you make this area really small, so that it's as small as a point, we call that as the static pressure. So right from its definition, static pressure is kind of predicated on the fact that this surface receives a lot of hits from a lot of molecules. So a macroscopic observable, I'm just trying to generalize it, a macroscopic observable is a physical manifestation of microscopic motion of atoms or molecules. What do I mean by that? At a microscopic level, an atom has only, at least classically speaking, has only position and velocity, neither of which you can actually see. You can't literally see an individual atom moving around. You only measure its physical manifestation at a macroscopic level. And now I'm going to ask you, what does macroscopic actually mean? When I say macroscopic and then when I say microscopic, what are you thinking?
So when we say macroscopic, it should be something measurable. So if we say macroscopic state of a system is we give P, volume, temperature, we can measure all of this. So, but for that particular macroscopic state, there could be million of microscopic quantities. So if you are going to describe a state, microscopic state, then all the molecules can have different types of velocity, and there can be different combinations. For all those combinations, we can describe it by just one microscopic state.
That's actually very nice. I'm sure you heard it, but what he is basically saying is, this is a average over lots of molecules, and the one thing you left out is, when we say macroscopic, the word macro actually refers to the fact that you are integrating over a length scale which is much larger than either the individual atoms or the length scale of their motion. Again, I'm going to draw a picture. Here's your, sorry, I need to tie my lace. Here's your fluid, static fluid, in which we defined static pressure. Okay. What is the microscopic or atomistic picture of this fluid? You have molecules or atoms that are undergoing random motion, and you can find a molecule that has a velocity. You can find another molecule which has exactly the same velocity or exactly opposite velocity. On a whole, these molecules are moving, but they have no net motion because their velocities basically cancel each other out. They are not systematically moving. Molecules are just randomly moving around. Okay? And if we say there are n atoms, I'm just going to use the word atoms, which could also mean molecules. Like I can talk about liquid helium or liquid water. I'm just going to use the word atoms to refer both. So there are n atoms, and each atom has a position and a velocity. Okay? And you can define the kinetic energy of each atom. Okay? If we take the average kinetic energy, that is what we call temperature. If we take the average momentum per area or average change in momentum per area, which is delta mv divided by A. That's what we call static pressure. So the simple concept is, you have so many atoms. Usually this number is of the order of 10 power 25. When you say 1 mole, that's already 10 power 23. So if you think of this room, at this moment there could be around 10 power 25 molecules that are zipping around. What he basically said is, you could have a bunch of atoms, each having their own velocity and speed. They all kind of average out to this number, which you call temperature, and more than one combination of these values for velocity can average to the same temperature. If you take a snapshot, like at this moment, if there was a magic instrument to measure the velocities of all the atoms in this room, and you do the averaging, they'll come out to, like, let's say 300 Kelvin. If you do this a little later, you will get a different set of values for the velocities, but they also will average out pretty much to the same temperature. So your temperature is kind of like a average over a large population. Okay, so what we see as a macroscopic observable is a physical manifestation of the microscopic motion, and not only that, it is over a length scale that is much larger than the length scale of motion of individual atoms. This again goes back to the very first lecture, where we said if you had molecules randomly moving around at around 1 atmospheric pressure, the mean free path is about 65 nanometers for nitrogen, or we'll say air. Mean free path, meaning if you are one of these molecules, on an average you can travel about 65 nanometers before which you will encounter a collision. On an average, which means some molecules may travel double this distance, or some molecules may travel only 1/10 of that distance, but on average basis, the mean free path is 65 nanometers. If your thermocouple probe tip is like a millimeter or a centimeter, over that length scale, you are much larger than this 65 nanometers. So your macroscopic averaging makes sense only when the length scale of your measurement or your quantity or your calculation is much larger than the motion of individual atoms. Think of the counter example. What if you make a probe tip which is only 10 nanometers in size? If I make a probe tip, okay, let's say this is the probe tip, and this radius is, let's say, 1 millimeter. On the same scale, if this is 1 millimeter, how big will 65 nanometers be? Okay, let's say 100 nanometers for simplicity, divided by 1 millimeter, that's 10 power minus 7 divided by 10 power minus 3, that's 10,000 times smaller. Like if I draw this to be this segment is, if I call this 1 millimeter, I have to draw a segment that's 10,000 times smaller than this. That would be 100 nanometers. You're with me that your gas molecule motion is extremely negligible compared to the probe tip. If you have a probe tip which is 10 nanometers, if this length represents 10 nanometers, how do I represent 65 nanometers? It has to be 6.5 times longer than this. So here is a molecule, and here is the next time it has a collision. In this case, the molecule only very infrequently hits this probe. So this probe never really has enough collisions with the molecule or doesn't meet numerous molecules. If you say that this probe has the same temperature of the gas, that is just plain wrong, because it's much smaller. It doesn't meet our criteria that the length scale is much larger. So whatever this probe is, it's not macroscopic because it's not larger than the length scale. Okay. Another counter example. You have a probe tip which is 1 millimeter in size. Suppose you are in the International Space Station and you take a spacewalk. You know what's a spacewalk, right? The astronauts tether themselves to the spacecraft or the space station, and they actually literally walk through space. Have you seen the movie Gravity? Some years back. Okay. So there the pressure is very low. Pressure is very low in the sense it could be as low as 10 power minus 6 Pascal. To give you a reference, atmospheric pressure is 10 power 5 Pascal. At 10 power 5 Pascal, dependent on how much or what is the density of the gas molecules, the mean free path is like 65 nanometers. And at this pressure, when pressure goes down, you know pressure scales with number density. Sorry, the other way. Number density goes down if pressure goes down. Okay? What happens at low pressure is that you could have your mean free path be as big as a kilometer. I will first let that sink in. To say that a gas molecule is here, it is moving through space at low pressure, the next time it might meet a molecule could be a kilometer away. Same probe tip, 1 millimeter probe tip. If this length is 1 millimeter, what is 1 kilometer? 10 power 3 meters divided by 10 power minus 3 meters or 10 power 6. I have to draw a line which is a million times longer than this. That's what will represent how often this probe tip collides with the gas molecule. So if you are in that scenario, to call that this tip is reading out a temperature is ludicrous, because that probe doesn't even collide with your gas molecules very often. So the basic condition for observing a macroscopic quantity is that first it should be an average over a large number of atoms. Same probe tip at atmospheric pressure satisfies that condition, but at low pressure does not. It should also be over a length scale that is much larger than the length scale of motion, which it satisfies at atmospheric pressure, but a smaller probe tip at atmospheric pressure does not. So two things you have to remember: large number, larger length scale. The reason I am saying that is, when you are going to use the principles of continuum mechanics, you just first have to ensure that your system has enough atoms in there. You can't use all the things that you learned in the course for a group of 3 atoms. It's just not possible. If your group of atoms has like 1,000 or 1,000,000 or 1,000,000,000 or 1,000,000,000,000, yes, you can apply the principles of continuum mechanics, or you can call it a macroscopic observer. If your length scale is not larger than individual atoms, you cannot apply this. Okay? What happens in that case? How do you deal with quantities which are not satisfying within the definition of a macroscopic observer? you treat them as individual quantities with or without quantum mechanics, depending on whether you see it as a classical problem or a non-classical problem. But at least the reason we are learning this course is because we don't want to describe a system in terms of all of its atoms. We want to approximate it to a few macroscopic observables like pressure, temperature, velocity field, position or displacement field, internal energy, entropy, and so on. So there is the state of a system, meaning at any given instant you can think of positions and velocities for all the atoms that make up that system, but it's not a very convenient way of talking about things. Why? Because there are just too many atoms. Who wants to handle 10 power 25 numbers of 10 power 25 velocities and positions? It's just a lot of numbers to throw around. That is why we define these macroscopic observables, number one. Number two, one of the other things that he said, you have to define a state for a system. Why do you need to define a state for a system? Or what is the state of a thermodynamic system? What have you learned in your prior classes about when you say the state of a gas or a state of a liquid? No, flow is something that's just like a form of motion. If you have a beaker of liquid water, or you have a cylinder of nitrogen, or the air in this room, or a piece of iron at a certain temperature, what do you understand by the word thermodynamic state?
Whether it's solid, liquid, or gas.
Whether it's solid, liquid, or gas, you are looking for some kind of information from the state. That is, the state should say, are you in a state of fluid or solid or something, right? But that is like visually saying, you can look at something and say it's a liquid or a solid or something. How do you quantify this? What variables do you typically use to quantify the state?
How, well, can we describe it with atoms or no?
We don't want to describe it with atoms because atoms are just too many. It's not easy to describe it in terms of that many high number of numbers. We use quantities. I'll give you the answer and ask you for the justification. We use quantities like temperature, pressure, volume, like you said, okay, specific volume. Why? What is the convenience that you get from describing? So if I bring a cylinder of air, compressed air, and I say the pressure in the gauge is like 100 kilopascal, or let's say 200 kilopascal, it's pressurized, and you bring a cylinder, your gauge reads again 200 kilopascal. What convenience do these variables give us to use them to describe the state of matter? Maybe I should put the question the other way. Suppose you do an experiment, you get a certain outcome. Like for example, this experiment I'm sure you have done in your high school, to put a gas and have a piston and you put weights around the piston, so that you are essentially setting the pressure in the gas and allowing the piston to move freely, so that depending on what the pressure of the gas is, it will occupy a certain volume, and you keep the temperature constant. And if you do this, you will get a relation that says pressure times volume is equal to the pressure times volume at two different conditions. That is, the fluid will follow a certain path in terms of its pressure volume relation. And this experiment is called, or this outcome is called, Boyle's law. It was probably discovered sometime in the 17th or 16th century or whatever, I don't know the exact date. But here's the question. If this experiment were done in a laboratory in Memphis or Chicago or Germany or Japan, there is a certain universality to this experiment. Not only this experiment, to any experiment. The whole of science works because it is irrelevant about who does the experiment or where the experiment is done. So what is the connection between doing the experiment at a given place, or how do you generalize the results from an experiment at a given location to another location, or a given experimenter to another experimenter?
You can completely describe the system using the variables you have. You can call it, those are the
State variables. That is, if the thermodynamic state of a material, which could be solid, liquid or gas, is completely described by a set of variables which we called state variables. Here's where they are called state variables, because suppose you take a particular point in here, okay, a combination of pressure and volume. If you reach that point, you could reach a point by starting from a higher pressure and working your way down, or you could reach the same point by starting at a lower pressure and working your way up. Once you reach that point, that material is defined by this pressure and volume combination. If the path by which you reach that point did not matter, that point so the path by which this state was attained is not or does not influence the value of a variable, then that variable may be used to denote the state of the material, and that's why we call it state variable. It's like saying like this: if you attain, suppose the temperature in this room is 25 degrees Celsius, 1 atmospheric pressure. Before I came in, the room was hot. I turned on the air conditioner and it came to 25 degrees and 1 atmosphere. On a different day, in a winter day, the room might have been very cold. We might have to heat up the room to bring it to the same state. At the end of the day, if it matters that your state is described only by the pressure and temperature and not by whether you had to heat it or cool it, then those two variables describe the state and not the path. Okay? It would make more sense to then think about, what about the path? What about the path? What are some quantities which depend on the way in which you execute that process and not about the outcome? Like, for example, can you think about quantities which depend on the path?
density?
Density is also a state variable, as we'll see, because density is related to pressure and volume and temperature. We can write P is equal to NKT, where N is number density. So it is also a state variable. Once you attain the density, or once you fix pressure and temperature, density cannot assume a separate value.
I was thinking there's like pockets in the solid. So would that not count?
Sure, but I'm just, we are talking about very simple materials to illustrate a point. What I'm trying to get at is, in the example I gave you, like this room, you have to either heat the room or cool the room to come to a certain state. If I ask you about the heat change or the heat flow from this room, in a winter day, we would be adding heat to the room. In a summer day, we would be subtracting or removing heat from the room. So if you think of heat change, that is a quantity which depends on path. It depends on whether you are heating or cooling. Whereas the outcome or the state you want to attain is independent of whether you had to heat or cool. Once you reach that pressure, you define the material there. You don't care how you got there. So the three concepts that I am introducing today: microscopic versus macroscopic observables. At a fundamental level, materials are made up of discrete atoms. Their physical manifestations as observables is over a length scale that is much larger than the motion, as well as due to a large number of atoms. The collective effect is called macroscopic observables. The second concept is, you can assume that, or you can take that all the atoms together determine the state of a system, and if the state of the system is independent, or if a quantity is independent of the path but depends only on the current state of the system, we call it a state variable. And those quantities which depend on the sequence or the path in which you attain those values, those are called path variables. Example of a path variable is work done. What is work done? Work done is force times displacement over a certain path. Or heating power or thermal power, or I would say heat transfer. Heating or cooling. Okay, the book has a definition for state variables which I'm going to read out. The macroscopic observables that are well defined and single valued when the system is in a state of thermodynamic equilibrium are called state variables. Those state variables which are related to the kinematics of the system, such as volume, strain, etc., are called kinematic state variables. Okay, so again, it's basically saying the same thing in slightly different words. So if at a basic level, what atoms have is only motion. That is the way our universe works. And I say our universe as though there are like multiple universes. But the way our universe works is, all atoms seem to have a perpetual motion of trying to move around randomly until we force them to move in a systematic way. That's how it is. So these atoms, okay, some move faster, some move slower. In a given population, there is always a distribution. And this population, the average kinetic energy of that population is what we call temperature. So when you have a hotter fluid and a colder fluid, this is basically a population that has a higher average and this is a population that has a lower average. Okay. Can we use this thought experiment where you have a beaker of hotter fluid and a beaker of colder fluid, T1, T2, where T1 is greater than T2, to define what is called as thermal equilibrium? Or in other words, you take the hotter fluid and colder fluid and mix them. In everyday experience, you know what will happen next. What will happen?
The temperature of the water
Has to come down, the colder has to go up, and they kind of average each other out. What is going on at a molecular level?
The impacts of the molecules are like the hot molecules are moving faster, so they impact with the cold
slow
molecules, and then they'll average, basically like transfer momentum, or yeah, just like the impacts overall over time.
So literally what happens is you have a slow mover, you have a fast mover. When the fast mover hits the slow mover, you are essentially kicking. You are literally kicking. So you give up some of your energy to the slow mover or somebody who is at rest, and they pick up their velocity, whereas you lose some. So the group that was hotter has to come down in energy or come down in temperature, and the group that was slower has to come up in energy or come up in temperature. This is if you literally mix them. Okay? Suppose you take the two beakers and you put them next to each other, and we'll assume the wall that separates the two beakers allows heat to pass through, but does not allow the molecules themselves to go through. So I'm thinking of an experiment here where I have a chamber. I put the hotter group here, T1 and T2, where T1 is greater than T2. And then here is the colder fluid. Okay, we put them next to each other. Somehow the heat can pass through, but the material cannot pass through. What will happen here? Or what is happening here is eventually the temperatures will come to the same value, but in terms of the molecular motion, they basically give up, this has to give up some of its energy, this has to gain some of the energy. And of course there is a wall in between, so the understanding is the molecules will collide with the wall, transfer some of their momentum, which is transmitted to the other side. Okay? We define thermal equilibrium in this way, where if you say two temperatures are equal, they don't have to literally be mixed together, but it is a state in which the average kinetic energies of the two sides are equal. Number one. That doesn't mean it is the same material on both sides. When you take a thermometer and you stick it under your tongue and you read a certain temperature, it basically is the temperature of your body or your whatever inside. It allows you to read out the temperature without having to put the material of the thermometer inside you, right? So thermal equilibrium is a state where the average kinetic energy of two populations are equal, and it allows us to define temperature. How? If one of these is a reference that you define as temperature, if these two are at equal temperature, then you say T1 is also same as T2. And what is that reference temperature? How do you define references? Can you give me one very common example of a reference temperature?
human body temperature 98.6.
That's not universal. Your body might have 98, somebody else might have 97, 99.
volume of water. And then you say.
So a pure material, in our case water, a pure material has a certain temperature at which it undergoes phase change, like melting or boiling, and we use that to define a temperature scale. So if we define ice point, that is, if you take a bucket of ice, until the last bit of ice melts out completely, the whole temperature will be at 0 degrees Celsius. So use one of those as a reference to measure the temperature of the other with respect to the reference. Okay? So it's all what is microscopic, macroscopic, what is a state variable, and that state variable is typically defined in terms of temperature, pressure, and volume. And then we also saw what is temperature or what is thermal equilibrium. Up to what I have discussed here is section 5.1 and 5.2. So as you can see, this is all kind of semi-qualitative, and the problems or the numerical problems we will do will be based on section 5.3. So in the exam, if at all there is going to be a conceptual question, you can expect it from section 5.1 and 5.2 related to the concepts of what is macroscopic variables, what are state variables, and what is thermodynamic or thermal equilibrium. Okay. I want to discuss a concept which started out as something that is core in thermodynamics, but as human understanding of other topics has evolved, has become much more prevalent in other fields, especially like in computer science, called entropy. Okay, you have heard of this word entropy, just like you have heard of the word energy. How do you think about entropy? Calculating entropy or measuring entropy, let's not even go there. In your understanding, what is entropy?
Degree of order.
Okay, that's easy to say, degree of order or degree of disorder. How would you explain? Like, that doesn't explain what is order. If you're using a term, you should define that, right? So, go further.
So you want it for just this class or every class?
Whatever you know about entropy.
Where things move towards more disorder, generally. I know that.
Okay, then what is order? What is disorder?
Organization of things, like it would require more energy to organize things in a lot of cases, and it releases energy when things become more disorganized.
If you're thinking about, let's say, ice, if you take solid ice and you supply energy, it melts and becomes liquid. So, by your definition, a solid should be more orderly than a liquid. Why? Because in a solid, the atoms or molecules are localized to specific sites. They can't move around. They can only vibrate in wherever they are locked in. And if you supply energy, you are helping them break bonds, and they start walking around. They transition to a disordered state or a random state where they can randomly keep bumping around, and you transition to a liquid. By your definition, a solid is more orderly than a liquid. And if you say, did you say entropy is a measure of order or disorder?
Disorder. Wait, yeah, disorder.
So the solid or the liquid, which has more entropy?
The liquid.
The liquid. The liquid is more disorderly. Okay. All right. So that sort of is correct, that a liquid is more disorderly. But how do you kind of think about entropy, or how would you go about quantifying entropy at least in a limited sense, so that we can understand how it is mathematically calculated. How do you quantify entropy? Suppose you are in your dorm room and you are a person who likes keeping things very organized. You have a rack for everything, you put your books away, your bed is nice and well made, as opposed to another person who just leaves everything in a cluttered mess. You walk in, the common phrase is, oh my god, the entropy in this room is higher than the other room. We always kind of associate disorder with entropy. Okay? How would you quantify it in a system which is made up of atoms? What constitutes order? What constitutes disorder? Yeah.
The amount of energy which is not available to this work.
The amount of energy that is not available to do useful work. Okay, nice. Can you elaborate a little further? I like
It
it.
relates to the total energy and which the energy which is not available.
Okay, I'll take that and try to expand on that. And these are your words. I'm just going to give you an example that fits with your definition. Suppose there is a piston. You put a fluid like a gas, hot gas next to the piston. The molecules are all randomly moving around. So at any given time, a small fraction of the molecules will be impinging on the piston, trying to move it forward. Try to move forward or move in this direction. But a majority of them will have their velocities pointed the other way. So you can't expect the piston to actually move because only a small portion are exerting force on it. Think of the other case where suppose you had a fan and the fan is pushing all the molecules along one direction. So that every molecule you can think of has a random velocity which is pointed in some direction, and the fan is giving it a directed velocity towards the piston. So in that case you would expect the piston to move because you are transferring a lot of mechanical energy to the piston through the molecules, each molecule having a directed velocity. So what he is saying is perhaps if you had the same energy content, suppose you had 100% energy and let's say all of the energy is in random motion. What is random motion? So if I take a molecule, I equals 1 to n, I have Vi, that is it has a velocity. Okay, you can write Vi is equal to V directed velocity plus V random velocity. Okay, so if you take a molecule, let's say it is being pushed in this direction and it also has a random component, and every molecule has its own random value, but all of them have the same directed value or the value with which the fan is pushing them. Okay, what is the total kinetic energy? Half m Vi squared. Okay, so if you consider this half m Vd plus Vri dot Vd plus Vri. Suppose there is no directed velocity, that is, consider the case Vd is 0. All the energy is present in all possible directions, so it's not going to help you do work. That's what you said. If by magic they don't have any random component and all their energy is stored in the directed component, then all the energy is available to describe it. And here is the difference. If I have n molecules and let's say n is a very large number, I need to have n numbers to describe the entire velocity distribution. But I need to have only one number to describe the directed velocity. So if consider the two extremes, all molecules have only random motion and no directed or systematic motion. In that case, how many numbers do you need to describe their velocities? They have n velocities and each velocity has 3 components, so you need 3n numbers. With me so far? And then the other extreme is they have no random motion and only directed motion. You don't need to describe the random component because there is nothing. So this is 0. And how many numbers do you need to describe the directed motion? All of them have the same velocity pointing one way. Just 3. That's 3 into 1. 3. So which is the orderly state and which is the disorderly state? This is orderly because you need very few numbers to describe the state, and then you need a large number of numbers, in fact the maximum number of numbers to describe this state. Okay? Suppose you can make a generalization that the reality is somewhere in between. That is, not all of them have the same, not all of them have no random motion, they all have some random motion, but you can describe it with lesser than 3n numbers. I'll give you one more example. At the end of it, you are going to tell me what the definition of entropy is. You take a solid. Okay. Let's consider 2 different temperatures. This temperature is around some temperature less than its melting point. Let's say minus 10 degrees Celsius, and we are talking about ice. And this temperature is somehow equal to absolute 0, where this is something like minus 273.15 degrees Celsius, which is not even a real temperature, and that's because this 0 Kelvin is not something that exists in reality. It's again an idealization we define. It's like a mystical state of matter where we say all motion ceases and the atoms are at rest. If it's a crystalline solid and all atoms are at rest, if you know the position of 1 and you know the lattice parameter, you can work out the position of everything else. There is complete predictability. How many numbers do you need to describe this solid, this perfect 0 Kelvin solid? Which is the lattice parameter. If you know the lattice parameter, you can pick any one and you can predict where everything else is relative to that one. If you take a real material at a finite temperature, the atoms, maybe they are vibrating, so their motion can, at any given time, an atom can be here or here. So you have each atom vibrating in its position, and if you consider that they are greater than the melting point, you are in a liquid regime where the atom is not just vibrating, it might freely move around. So the disorder only increases as you increase the temperature. How many numbers do you need to describe this? Exactly 1. And anything else will be more than 1, or in other words, this is the state where order is maximum or entropy is minimum. And now if we take your first definition to say that entropy is a measure of disorder and it increases with it increases with temperature in general, can we now generalize what entropy is or how to calculate entropy? One more example, yeah.
Sorry. Normally it is the heat observed constant.
Okay, I'm before we go to heat and how heat is related to this, I want a statistical definition or statistical way of thinking about entropy. Let me give you an example. How many of us are here? 3, 6, 7. 7 people. Okay. If on any given day you all take seats that I don't control or I don't know, I can't predict. But if for some reason the 7 of you sit exactly in this row, there are 7 seats. Let's say there are 7 seats here. If you just sit in this 7 starting from there to here, it's easy for me to write a law or a generalization of your seating position. It starts there, it runs for the next 7 positions. So I need exactly 2 numbers, one specifying the starting position and another specifying the number of people. So I can describe your seating positions with exactly 2 numbers, as opposed to, let's say today you are all seated this way, tomorrow you are all seated in some other pattern, some other pattern. Every time there are many ways you can seat yourself if you are doing this randomly. Count the number of seats. Let's say there are 40 seats and 7 people. You can sit in 40 P7 permutations on any given day. So entropy you can think of as a quantity which scales with the number of ways a system can be configured or arranged. This system can only be configured, or this system's configuration is described by exactly one parameter, lattice space. If you had a bunch of molecules and each have their continuous velocity and continuous position, you can think of how many numbers do you need to describe all possible states or all possible configuration. I'll tell you what I mean by configuration. You have x1, x2, x3, xn, v1, v2, v3, vn. If you take a combination of these 2n vectors or 6n components, you take one combination or one snapshot, you get 6n numbers. That defines a state. You let time pass or some other later instant, you take another snapshot, you get another combination that is a different state. How many possible configurations can these states assume? Practically infinite, because these are all continuous quantities. It can take 1, 1.0, 1.00 and so on. So that is not the question. The question is, if you take or if you sample this quantity once, twice or a finite number of times, you are sampling 1 out of a population. And depending on, let's say you sample enough number of times, you can represent the population as a histogram or a probability density. Okay? So entropy at the end of the day comes down to, if you sample a certain population enough number of times, the number of parameters or number of combinations that appear in that sampling is what entropy is about. A less disorderly system has fewer parameters or fewer possibilities. A more entropic system or a more disordered system has more ways in which it can exist. That again comes back to your ice and water. If you know the molecule is ice, if you know it is at a certain temperature, you can predict its lattice structure, or people have studied its lattice structure. And once you know the lattice structure, it's like a repeating cell. You know the unit cell, you know that relative to one molecule, the other molecules are in certain coordinates. You can repeat that infinitely. That is in an ordered state, but if you take a beaker of water, it's almost impossible to say how many possible configurations there are. That's why it makes it more higher entropy than a ice. Okay, so the third concept that I've been, so one is this macroscopic and microscopic, the other is state variables, and now we are introducing, we also introduced thermal equilibrium. Now we are introducing what is entropy. So I will give you my definition and then also read the definition from the book. Entropy is the number of combinations in which, entropy is the number of combinations in which a system can exist. Fewer combinations, meaning lower entropy. The limiting example is the 0 Kelvin solid, which is like a idealization. More combinations imply higher entropy. This idea, a summary of what what I discussed is basically in section 5.5, which is related to entropy. So we saw section 5.1, 5.2, and then we jumped to 5.5. Okay. So we didn't get a lot of, I should say, my course planning didn't allow me a lot of time to discuss thermodynamics in greater detail because we spent a lot of time in kinematics, and then we did spend some time in momentum and mass conservation. But to at least touch those concepts, I wanted to introduce what is entropy, and I want you to be qualitatively familiar with it, but more quantitative problem solving will be focused on mass and momentum conservation. Okay, just to keep it organized for your exam. Whatever we saw, in chapter 4, section 4.1, which is mass conservation, and section 4.2, which is momentum conservation, and then section 5.1, 5.2, and 5.5 talks about thermodynamics, but you can expect only qualitative or conceptual questions in this, and more quantitative questions related to this. Okay, only conceptual questions. For example, problem 5.2. If you have the book in front of you, please look at 5.2. It's a very long problem statement. I'll give you 2 minutes to read that, and then we'll discuss it. So a solid is put in contact with a hot gas, and there are like, you can look at the problem statement, but essentially it's like a rectangular slab in contact with a hot gas, and one of the dimensions is constrained, like putting it in between two supports, the two rigid supports. So the only possible way this solid can expand is in the other direction, the L2 direction. Question is, do you expect L2 and or volume to change? Why or why not? That is, if you transfer heat to this solid which is constrained between two supports, do you expect expansion in the lateral dimension? Yes or no? That is the question, really speaking. If you transfer thermal energy to a solid, what happens at an atomic or atomic level?
More vibration.
The vibration becomes higher in amplitude, and in an extreme case, as you keep transferring more heat, they transition to becoming a fluid. But we are not going there. We are just applying a little more heat, like going from 50 degrees to 70 degrees or something like that. So the atoms vibrate even further, and that will cause what? No, we are not supplying enough thermal energy for the atoms to completely break away. We are just making the atoms, think of them as little pendulums. Instead of oscillating at a certain amplitude, we are making them oscillate at a larger amplitude. If the entire material is forced to oscillate, or the atoms are forced to oscillate higher amplitudes, what does that mean macroscopically is the question. If all atoms undergo a wider or a more a higher amplitude motion, how will that manifest physically or macroscopically? It could mean higher temperature, and from everyday experience, you know that higher temperature also comes with thermal expansion. Can you, and my question to you will be something like this. You are given an observation like thermal expansion. How do you explain thermal expansion in terms of atomic motion? What is thermal expansion macroscopically, and how does it tie back to what the atoms do when they are given more energy?
The vibrations are going to displace atoms slightly further away.
So their mean separation will slightly increase, making them increase their effective volume, which is what we see physically as expansion. So if you add a length measure, the length would literally go higher because the atoms now themselves have pushed each other apart, and if everybody does this, then the overall length will increase. This is the kind of questioning you can expect in the exam. You will be given an observation, and you will be told, or you will be asked to say what will happen macroscopically and explain this in terms of atomic motion or what happens at a microscopic level, just to give you a sample question. Okay, so I'll stop here today. On Tuesday, the goal is to do some model exercises that are similar to the homework, as well as some examples in which will give you an idea about what to expect in the exam. Of course, the exam is take home. You get like a week to do that, but I just want to go through typical problems or a mock exam that you can expect. Okay, so take a look at the homework 3. Please attempt, and if you have some questions, Tuesday is the time we can discuss it out. All right, so we'll try to wrap up the course on Tuesday. Thank you.
Is the homework due Tuesday?
Homework is due the following day, Wednesday, by Canvas. Please don't email me, just upload it through Canvas.